Hi, welcome to this video. A couple of people have been requesting me to start looking at energies and periodic table and sort of more physical side of chemistry, which I think is definitely a good idea to cover. So I'm not stopping, but for the next probably 2 or 3 weeks, I'm just going to be postponing videos on organic and inorganic chemistry and just sort of focusing down on this physical chemistry. And the first major topic we really have to cover before getting into the nitty gritty. Don't know what I'm talking about. The grits of ionization energy, enthalpy, trends, periodic table, tests of ions, for example, etc. First topic we really need to cover is shells and orbitals, and an introduction to sort of electron configuration. But I'll look mainly at electron configuration in another video. We're going to mainly be focusing on this thing called the quantum number. Now, the quantum number sounds all fancy because it's got this quantum in it, but really don't let that scare you whatsoever. This is quite simple, and it's known as a principal quantum number, and it's defined as n. And what n is really just different shells have different quantum numbers. For example, let's look at hydrogen. Hydrogen has got one shell. Hydrogen's got one shell here, and in that shell you've got one electron. So this first shell here is given the quantum number n of 1. And so you can see that it's quite simple. Each shell is given its number. For example, shell 1 is n1, shell 2 is just 2, shell 3 is 3, shell 4 is 4. And so we can sort of say here that for n, this is shell 1, 2, 3, 4. This is obviously going to be the first shell, second, third, fourth, and so on. And really what we just want to find from this are the number of electrons. In each shell. And you're not typically taught this in A-level, but I think it's quite useful to know, is a sort of neat little formula you can use to quickly find out the number of electrons per shell. So if I start writing down some of the values here, you might be able to figure out some sort of formula yourself. But if not, don't worry. We maybe go to 5. Yes. We're just going to be doing you don't really get past 4, really. You don't really get past 4, but I'm just using these as an example. So, if you haven't guessed it already, the formula used is 2n squared. And so you can see, as n is defined as 1, we have 1 squared is 1, 2 times 1 is 1. For 2, for example, we have our n is 2, 2 squared is 4, 2 times 4 is 8. It's as simple as that. So that's really all you have to know about the different shells or or energy levels per se, as I know some people like to define them. The second thing I just want to cover in this video are orbitals. Now, I'm only going to draw two of the orbitals because, well, I don't think I could draw the other two orbitals, but, well, as you guess now, there are 4 orbitals, and the orbitals are S, P, D, and F. And I think something neat to talk about, which is often talked about later on in chemistry, but it should be noted, I think, at this point. Before I even tell you what these orbitals are, I'm going to break the periodic table down into 4 sections here. Very lovely periodic table, and try and get a blank picture of a periodic table if you can. Just draw helium up here and fill it out as I go along. So here in group 1 and group 2 we're going to have the S the S block. This is the S block, and helium here is also inclusive of the S block, even though it is part of the group 0, group 18. And then we have the P block. This is P block, and this is inclusive of pretty much all of the non-metal elements. Then we have transition metals, which are in the D block. This is D, and here we have F block elements. And this is quite neat when you're coming on to quickly working out electron configurations of elements. But for now, I just want to give a sort of summary of what we're actually talking about here. So if I talk to you about the S orbital is simply the shape of a sphere. And each orbital it's complicated to think about in the fact that the S orbital gives up to 2 electrons. Okay, so it's almost like the first shell, sorry. So we see that from n upwards, from n equals 1 upwards, we say each shell contains 1 S orbital. So it's not exactly it's not to do with the shells. The orbitals are arbitrary from the shells. Each shell, N1, N2, N3, N4, contains 1 S orbital. And each S orbital can hold up to 2 electrons. For example, we can see with helium that I know I haven't covered this, but its electron configuration is 1s2. And that's because we know helium has 1 shell. We know helium's got 1 shell. And we know helium also has 2 electrons. But for N1, there's only 1 orbital, and that is the S orbital. And so the S orbital can hold up to 2 electrons. And this is where we start coming into sort of ionization energies and stuff like that, for example, where there's sort of imbalance, stuff react in different ways, for example, but I'm not going to go too deep into that right now. But yes, s orbital, 2 elements, 2 electrons. Sorry. Next, we're going to look at the p orbital. So, I want to clarify what I was talking about, just in case it's a bit confusing. Say, for example, if n equals 1, which is the number of shells, then there's 1 shell around that element, which means there's only going to be an s orbital. But if n equals 2, then we're going to have a 1s orbital, and we're going to have a 2s orbital. So they're sort of cumulative in that sense. So if n equals 3, we're going to have a 1s orbital, a 2s orbital, and a 3s orbital. Obviously, there are more orbitals than that, because, I mean, there's up to 18 electrons in the third shell, but we'll get to that in a second. So, p orbital. The p orbitals, per se. There are 3 p orbitals, and these are really just defined as px, py, and pz, and don't let that be confusing. This just works in terms of geometry, almost like vectors per se, but yeah. So this is obviously y, this is z, this is x, and p orbitals have this dumbbell shape. So here's our px, here is our pz, really should have drawn these maybe separately, and here is our py. And for each p orbital, they can hold up to, each p orbital holds up to 2 electrons. So we know for each individual orbital, it can hold up to 2 electrons. So the maximum the p orbitals can hold up to are p6, 6 electrons. So when we see something like for example, when n equals 2, p orbitals are present in elements with 2 or more shells. That's an easier way of looking at it. Okay, so when we see an element where they have 2 shells or more, maybe they have 1, 2, 3, 4, maybe they have 10 electrons. Okay, maybe they have 10 electrons. I mean, that's obviously neon, but yeah. Say we have neon, it's obviously going to have its 1s orbital, then it's going to have its 2s orbital, because remember, in the first shell, it only holds up to 2 electrons, there's only an s, but from 2n upwards, we're going to have 2s, but we're also going to have 2p. And we can see as the electrons fill, we know there's 2 electrons in the first shell, and we also know there's going to be 8 electrons in the next shell to make its 10 electrons. So we're going to have this 2s2, because there's only a maximum of 2 electrons in the s orbital, because it is just 1 orbital, whereas in p, there's 3 orbitals for p, to define p, so we know that there will be a total of 6 electrons, like so. And this is obviously looking at electron configuration, but in my opinion, this is the easiest way to explain it. I think next up, we obviously have our d and f orbitals. I'm not going to draw these because these are very complicated, but just note that from n3 upwards, each shell contains, and there are 5 total d orbitals, and there are 7 total f orbitals, and for that means there's obviously 7 times 2, which means the f can hold up to 14 possible electrons. D can obviously hold up to 10 possible electrons, and so forth. But remember, this is cumulative. So if we had maybe n equals 3, and let's choose the next gas, we have maybe argon, or n equals 3, where we would have 1s, then 2s, then 2p, and then we have sort of 3s, then 3p, and it does go to 3d, but not for argon. So, and I'm going to talk about this more in the next video, but obviously you're probably thinking now, what about the 4s? But then in the D's, is it 3D or is it 4D in the periodic table? Let me go to this periodic table I've drawn here. Really, this here is the 3D, and this here is the 4s. And I know this is not a very scientific way of looking at it, but in my opinion, for a student to learn, this is probably easier. But here, just 3D 4s orbital fills with electrons before 3D, and that is because the 4s orbital gets filled first because it has lower energy, right? It's higher energy gets filled after. Okay, but also think about it in the order of the periodic table, right? We have here 3p, and then it goes to 4s, and then 3d. So think it gets filled first, but when writing it out, it's scientifically correct to do 3p. To write out as 3p, 3d, 4s, it gets confusing like this. But that's scientifically correct. That's how it's supposed to be. But just note the electrons will fill in the 4s orbital before they fill any of the 3D orbitals. And yes, now in the next video I'm just going to cover spin of electrons, which is very important, and so different ways we can represent electrons in orbitals, for example in boxes, things like that. And then I'm also going to cover electron configuration. So thanks for watching, and hopefully this was less confusing than I think it is. If it was confusing, just comment in the comments and I'll try and make shorter versions of this video explaining different individual parts.